Every week brings new claims about AI advances. How do we know what's coming next? Could AI predict crime? Write award-winning novels? Hack into critical infrastructure? Will we finally have robots in our home that will fold our clothes and load our dishwashers? What will AI advances mean for your job? What will it mean for the social fabric? It's hard to deal with all this uncertainty. If only we had a way to predict which AI advances will be developed soon and which ones will remain hard for the foreseeable future. Historically, AI researchers' predictions about progress in AI abilities have been pretty bad. We don't really have principles that describe which kinds of tasks are easy for AI and which ones are hard. Well, we have one.
Moravec's paradox.
Moravec's paradox. Moravec's paradox.
Moravec's paradox.
Moravec's paradox.
Moravec's paradox.
Moravec's paradox.
Moravec's paradox.
Moravec's paradox.
Hi, my name is Arvind Narayanan. I'm a professor of computer science at Princeton University. Moravec's paradox is the observation that it's easy to train AI to do things that people find hard, like math and logic, and hard to train AI to do things that we find quite easy, like seeing the world or walking. It comes from a 1988 book, Mind Children, by Hans Moravec, who was and is a robotics researcher. He wrote, "It is comparatively easy to make computers exhibit adult-level performance on intelligence tests or playing checkers, and difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility." In the early days of artificial intelligence, researchers focused on chess and other reasoning tasks since these were thought to be some of the hardest and what made us uniquely human. But funnily enough, if you want to build a robot that can defeat human grandmasters, figuring out which moves to make turns out to be the easy part, and physically making those moves on the chessboard turns out to be the hard part. This is pretty well known today, so Moravec's paradox seems to make a lot of intuitive sense. If Moravec's paradox were true, the implications would be amazing. We would know which AI capabilities might be built next simply by seeing how hard they are for humans. So, scientific research will get automated before folding clothes, and so on. But here's the thing. Moravec's paradox has never been fact-checked. And that's despite videos with hundreds of thousands of views and TED Talks all repeating it as a fact. When I dug into the evidence behind the so-called paradox, I found something surprising. In this video, I'll show you why the theory and evidence behind Moravec's paradox are flaky. Then, I'll explain why simplistic predictions about what's easy or hard for AI have misled AI researchers and tech leaders. It has led to alarmism on the one hand, and at the same time, false comfort on the other hand. Now there's a paradox. And finally, I'll answer the question, if we can't rely on Moravec's paradox, then how should we prepare for AI advances and their impacts? How would we test Moravec's paradox? We could take some sample of the tasks that are out there, determine how hard they are for people, how hard they are for AI, and make a graph. If we saw something like this, the paradox would be confirmed. There are an endless number of tasks that are easy for both humans and AI, but they're not interesting. How bright is an image? How to play tic-tac-toe? Thousands of these tasks get solved by programmers on a daily basis and coded into AI systems, and when programmers do so, they don't make a fuss about them. There are also an endless number of tasks that are hard for humans, and as far as anyone knows, are also hard for AI. Identifying hit songs, predicting stock prices, cracking ancient scripts that are as yet undeciphered, even building a Dyson sphere. These are so hard that there is essentially no progress on these problems, although some of them attract junk research that tends to quickly get debunked. So these problems also don't get talked about as much. In fact, there are thousands of problems that computer scientists have proved to be quote-unquote NP-complete, which means that we have strong mathematical reasons to think they will forever be hard for AI. So, serious AI researchers don't tend to work on them. They work on easier, approximate versions of the problems instead. The other two quadrants of the chart are different. Tasks like playing soccer, that are easy for humans but currently hard for AI, are extremely interesting to AI researchers. That's because we know it's possible to teach AI these skills, but we haven't managed to do that yet, which makes them great tests for AI progress. Problems that are hard for humans, but easy for AI, such as searching the web, are also interesting. These capabilities tend to greatly augment human productivity. Even though they are in some sense easy, the industry invests a lot in making tasks like web search work as effectively and quickly and cheaply as possible. So, research on these tasks is a big driver of AI progress. In short, when you're thinking about the space of all possible tasks, if you basically ignore 2 quadrants of your 2x2 matrix because they're not interesting, then of course it will seem like what you're left with shows a strong negative correlation between the 2 axes. In other words, Moravec's paradox is really a statement about which problems the AI community finds it worthwhile to work on. It doesn't have any predictive power over what's going to be easy or hard for AI. To be clear, the reason AI researchers are drawn to Moravec's paradox isn't because it's empirically backed. It's because it comes with an intuitively appealing story. In his book, Moravec provided this explanation. Encoded in the large, highly evolved sensory and motor portions of the human brain is 1 billion years of experience about the nature of the world and how to survive in it. The deliberate process we call reasoning is, I believe, the thinnest veneer of human thought, effective only because it is supported by this much older and much more powerful, though usually unconscious, sensory motor knowledge. We are all prodigious Olympians in perceptual and motor areas. So good that we make the difficult look easy. Abstract thought, though, is a new trick, perhaps less than 100,000 years old. We have not yet mastered it. It is not all that intrinsically difficult, it just seems so when we do it. And then Moravec praises reasoning systems like strips from the 1970s, and this is the kind of thing he has in mind when he says that reasoning is easy for AI. These are purely symbolic systems that solve problems like how to put blocks on top of each other in a certain way. But AI researchers have learned a lot in the half-century since the heyday of strips and other such reasoning programs. These seem to be quite quaint by today's standards. What we've learned is that symbolic reasoning only works well in closed and extremely narrow domains like chess with a fully specified set of rules. When you apply them to real-world problems, they quickly go off the rails. Over the decades, there have been many other failures of reasoning systems, like IBM's Watson, that excelled in narrow demonstrations, but failed when you tried to put it to use in real-world settings that could depart from what it is trained for. Today, it's widely recognized that reasoning in open-ended settings requires common sense knowledge. But common sense is one of those so-called easy for humans but hard for AI areas, according to acolytes of Moravec's paradox. In other words, AI reasoning isn't easy after all. And sure enough, AI reasoning in a way that can replace human expertise in domains like law or scientific research that are open-ended, that's still very much unsolved. If I were to speculate where Moravec's evolutionary argument goes wrong, it would be this. Reasoning might be new from an evolutionary perspective, but it builds on the things that animal brains have learned to do over hundreds of millions of years. This much Moravec acknowledges. But maybe there isn't a separate skill called abstract reasoning that can be learned separately without all of this infrastructure. Unfortunately, partly because of the misconception in the AI world that reasoning is a separate skill that's easy for humans, there is a widespread belief that AI will soon be superhuman at things like scientific research or operating a company or even a government. In my experience, many researchers tend to generalize from AI success at chess and other closed domains to these kinds of open-ended domains. Much of my writing is based on the idea that superhuman AI reasoning is a myth. Of course, you don't have to accept this. But when you hear these predictions of imminent superintelligence, it's helpful to understand the underlying mental model that many people in the AI field have that generates these predictions. And it's definitely useful to know that we have 5 or 6 decades of evidence that whether such a skill as reasoning is easy or hard for AI can depend a lot on whether you're talking about a closed domain or an open domain. Now let's look at the other side of the coin. Some capabilities are predicted to be hard because of Moravec's paradox. Most frequently, it's robotics. Just as people say we have to worry about job losses and safety implications of breakthroughs in reasoning, they'll say we don't have to worry about job losses and safety risks of breakthroughs in robotics as much. It's a hard problem, so improvements won't happen overnight. Unfortunately, this is false comfort. Now, I could be wrong about what I said about reasoning earlier, and there could be a breakthrough tomorrow. Similarly, these researchers could be wrong about robotics, and there could be a breakthrough tomorrow. In fact, there's another quote-unquote hard problem for AI that used to be invoked in order to explain Moravec's paradox, and that's computer vision. But it doesn't get invoked anymore, and that's because there was in fact a breakthrough around 2012-2013 when AI performance at tasks like object recognition shot up dramatically due to what's called deep learning. The reason it even took that long, one reason at least, is that it required the use of GPUs, and the idea of using GPUs for AI only began around that time. The scientific ideas behind deep learning had largely been established in the 1980s, before Moravec published his book. He just didn't know it yet. There's a reason why rules of thumb like Moravec's paradox are so tempting. It's because we assume that if there were an AI capability breakthrough, there would be rapid societal effects such as job losses, so we have to be prepared in advance. But this isn't actually true. Even breakthrough technologies take a long time to be successfully commercialized and deployed. In fact, breakthrough technologies may especially take a long time to be deployed, because the supporting infrastructure just isn't there. There's a famous case study of why it took 40 years for electric power to replace steam power in factories. Consider self-driving cars. Waymo started testing them on public roads more than 15 years ago. There was little reason to doubt that this technology would one day be viable, and that it would have good and bad effects. Policymakers should have been preparing and figuring out how to compensate workers who stood to lose out. Instead, people are only now waking up to the reality that these cars and trucks are already on the road, and so they're pushing policies like banning self-driving vehicles. Keep in mind that 1 million people a year die in car accidents worldwide, and self-driving cars are already much safer than human drivers. A recurring theme of my work on AI is the difficulty of prediction, both the use of AI itself for prediction and predicting the future of AI capabilities and impacts. Instead of relying on prediction, we should get better at shaping and adapting to the tech that we actually know is coming. This can be psychologically hard to do, but if we let go of our need for prediction, we can build a much more resilient society.